Hi, it's Mr. Claudia here, and today we're going to be going through 4.3, which are tricky problems again, but this time problems involving friction. This is actually one of the last sections for Newton's laws, so these are kind of like the toughest types of Newton law questions you'll see in grade 11. Very similar to last chapter, when we have problems that involve multiple masses that are connected by rope, you're going to use the same strategy as last time, which is to make a series of equations. So make a Freebody diagram for each of the masses, and then make an equation using F net equals ma, and keeping in mind that the tension in any one rope is always the same, and the acceleration for all of the objects is all the same. You'll then be able to solve your system of equations and find your answer. So let's get started. Two masses are connected by a rope as seen below. The coefficient of kinetic friction between the masses and the ground is 0.21. So let's write that down right away. 0.21 is mu k. If a force of 6.4 newtons is applied to the left, determine the tension in the rope. Okay, so let's draw some free body diagrams. First up, I have mass number 1. So it has a force of gravity 1, and up here I have a force of normal 1. Okay, and then I have some sort of applied force pushing on it, or pulling on it, sorry, and that's 6.4 newtons to the left. Okay, is that it? No, because there's also this rope, this pesky rope that's pulling me backwards, so that would be the force of tension. But there's also friction, and again, if I'm pulling this way, there's some friction that fights me, and because I'm moving, it has to be kinetic friction. Now think about this. If I'm pulling these blocks, they're both moving in this direction, so they're accelerating in this direction. So these should not add up. It's not constant motion. We're going to assume it's not constant motion. So these should not add up to be the same. This is probably longer than these two because we know it's moving in this direction. Okay, this is FK1, and the FT is the same between these two. For mass 2, doesn't have anyone pulling on it, but it does have this rope force, FT, pulling on the other direction. There's some small amount of kinetic friction, FK2, and then there's some force of gravity, Fg2, and there's a normal force, Fn2. Note that the force of gravity and normal they should be smaller because this is a smaller mass. M1, as we know, is 1.5 kilograms. M2 is 0.93 kilograms. Okay. All right, so now we have to solve this. So it looks a lot like the questions from the end of chapter 3. We're going to assume that the acceleration of both of these is the same, and we're going to use that to make two separate equations. So let's look at, for mass 1, let's look F net for mass 1 is equal to M1A, and then we have to add up all the forces, so we have FA plus FT plus FK1. Okay, so that's Newton's first or second law, and then this is F net, adding up all of the different forces. Now we should define some directions. So let's say to the right is positive, and let's say up is positive. Okay, so my mass is 1.5, and I have no idea, so I'm just going to write A. FA is to the left, so this is positive 6.4. FT, I don't know what it is, so I'm just going to call it FT, but I'm going to write it as not a vector because I know it's to the right, so I know it's a negative. And FK, should I be able to figure out FK? Oh yeah, I can, because I know the formula for FK. Okay, so it's got to be negative as well because it's going in the opposite direction. it needs to be mu k Fn. And I happen to know that Fn is going to be the same as Fg. So I actually can figure this out. Let me do a little aside over here. Fn is equal to Fn1 is equal to Fg1 is equal to mg. Again, I'm going to leave out the vector to show that I'm just doing scalar work here. So 1.5 times 9.8. Let's figure that out. 1.5 times 9.8. 14.7. Okay, so then I can sub that in. So I get 1.5a is equal to 6.4 minus ft minus 0.21 times 14.7. I can clean this up a little bit, so I'm going to multiply this by 0.21. 1.5a equals 6.4 minus ft minus 3.087. Notice how you decide the direction, right? The ft we know is to the right, so it's negative. Fk we know is to the right, so it's negative. What we did last time is we tried to get ft by itself. So 6.4 minus my answer. 1.5a is equal to 3.313 minus ft. I'm going to bring ft to the other side, and then I'm going to get 3.313 minus 1.5a. If you remember, we're going to get another equation for the second block, and we're going to be able to set the ft's equal to each other. So let's do that. Let's go over here and look at block number 2. Again, we're going to look at Fnet, block number 2, which is equal to mass 2 times acceleration. Remember, acceleration is the same for both blocks. And we're going to add up all the forces. That's Ft plus Fk2. Now, let's deal with these vectors. So this is going to be 0.93 times a. I know a is going to be positive because I know they're accelerating to the left. Ft, well, I know Ft is to the left, so it's going to be a positive value, whatever that value is. And Fk is to the right, so it's going to be negative. And we're going to use the formula, which is mu k Fn. Okay, what is Fn? Oh yeah, Fn2. Fn2 should balance Fg2. So I can do a little work over here. Fn2 is equal to Fg2, which is equal to m2 times g. So I get 0.93 times 9.8. Let's do that calculation. 0.93 times 9.8. 9.114 newtons. So when I sub this into my formula here, I get 0.938 is equal to Ft minus 0.21 times 9.114. Times 0.21. So I get 0.93a is equal to Ft minus 1.91394. So I get Ft is equal to 0.93a plus 1.91394. Whew, okay. So a lot of work to get here, but now look what I have. I have one equation with two unknowns, and I have two equations with the same two unknowns. So I can solve these using my grade 10 math strategies. What I'm going to use is substitution. So I'm going to set one equal to each other. 1 equal to 2. So I get 3.313 minus 1.5a is equal to 0.93a plus 1.91394. Okay, now I just need to solve for a. So I'm going to collect all the a's on this side. So I get 0.93a plus 1.5a. And I'm going to collect all the constants on this side. 313 minus 1.91394. I still have that number in my calculator, so I have 3.313 minus my answer. So we get 1.39906. And here I get 1.5 times 1.5 plus 0.93. That gives me 2.43a. So then I can divide 1.39906 divided by that answer, and I get A is equal to 0.5757. Great. I found out the acceleration of both blocks. What was it asking for? This question wasn't asking me for acceleration. It was asking me for the tension in the rope. So just like last time, I'm going to have to revisit one of these two equations and solve for Ft. So I'm going to sub in to equation 1. So Ft is equal to 3.313 minus 1.5 times 0.5757. I still have that number in my calculator, so I'm just going to multiply it by 1.5. And I'm going to take 3.313 and subtract the answer. So I get a tension of 2.449. Therefore, the tension in the rope is 2.4 newtons. And I don't need a direction because it's tension in the rope. We know for this block the tension's pulling to the right, and for this block the tension's pulling to the left. Does this number make sense? 2.4. Well, we know here that we're pulling with 6.4 newtons. We know that these two cannot be more than 6.4 newtons. There's approximately 3 newtons of friction, and then there's 2 newtons of tension. And so there's the leftover newton and a half of force is causing the acceleration. So the number makes sense. Phew, what a fun question. Okay, let's turn the page and let's look at the second type of problems you can have, which are problems that involve pulleys. And again, this is very similar to the end of chapter 3. We're going to make a free body diagram for each cart, or each object, and then we're going to be able to solve a system. So a 2.3 kilogram cart is attached to a hanging mass. Okay, so this is M1 is equal to 2.3 kilograms. And there's a hanging mass. The coefficient of static friction is 0.55. Determine the maximum hanging mass before the cart moves. So I need to figure out what M2 is. Because you imagine there's friction here. So if I put a feather and hang it from the pulley, well, nothing's going to happen. If I put, a slightly heavier thing, nothing's going to happen. The friction's going to hold me there. But eventually there's some weight that I can hang here that's going to cause this whole system to move, to start accelerating. The block is going to accelerate down, and the car is going to accelerate forward. The acceleration is going to be the same. Okay, so let's look at what that situation would be. Let me draw a free body diagram for just up to the point where the car starts moving. So you have to think I have a force of gravity, Fg1. I have Fn1. I have some sort of static friction force that's at its maximum right now. It's stopping me from moving. And that's being fought by my force of tension. But because this is just before moving, so just before movement, so this and this are going to balance because we have a at-rest situation. Similar, just before movement, we have this mass here, Fg2, and that's perfectly balanced by Ft. Now, I didn't really draw these correctly, but this and this are also the same length, right? Because this block is still at rest. These two are still balanced. And what's the question asking for? What is the maximum hanging mass? So I need to figure out what mass for this that's hanging here. To do that, I need to find Fg. To find Fg, well, I know Fg is the same as Ft. And from this free body diagram, I know that Ft is the same as Fs. And Fs I can find using the formula for static friction. So we have kind of a long backwards journey here. So let's say we know that Fg2 is equal in magnitude. Let me use the free body or the absolute value bars there just to show us. The magnitude of Fg2 is equal to the magnitude of tension which is equal to the magnitude of Fs1. So the question is, can I figure out what Fs1 is, what static friction is on the first mass? Well, Fs1 is equal to mu s Fn. Again, we don't need to use arrows because these are not vectors. We know what the static friction coefficient is, it's 0.55. But what's normal force? Normal force of 1. Well, normal force is the same as the force of gravity of 1, which I can figure out because I know the mass. So over here, the force of normal for car 1, the magnitude of that is equal to the magnitude of Fg1, which is equal to mg, m1g, which is equal to 2.3 times 9.8. So I get 22.54 newtons. That's my force of gravity, my normal force. So I can put that into this formula, 22.54 times 0.55. So I get 12.397 newtons. That's my static friction force. That also happens to be then Fg2. So I have Fg2 is equal to m2g. I know the force is 12.397. The mass is what I'm trying to figure out, and I know the acceleration due to gravity is 9.8. So if I divide 12 divided by 9.8, I get m2 is equal to 1.265. Therefore, the max mass is 1.3 kilograms. Think about it. If you have, that's the situation where you have the most amount of static friction force. As soon as you put any more mass onto this hanging weight, all of a sudden you're going to overcome static friction, and this is going to start going down, and this is going to start going to the right. Which leads us to our last question, which is question 3. A 2.3 kilogram cart is attached to a hanging mass of 3.8 kilograms. Okay, so M1 is equal to 2.3 kilograms. M2 is equal to 3.8 kilograms. The coefficient of kinetic friction is 0.45. Determine the acceleration of the cart. Remember, this is a system where you have the same tension in the rope, and this car is accelerating this way, and this mass is accelerating this way. They're accelerating at the same acceleration. Let me draw a free body diagram. So I have my force of gravity on the cart, the normal force of the cart. I have the tension force, which is pulling me this way, and then I have some small amount of kinetic friction that's pulling me backwards. For this mass, I have a larger force of gravity because it's heavier, and I have a force of tension pulling me backwards. There's no friction because I'm not contacting anything. And we know that the force of gravity is overpowering the force of tension because we know this block is accelerating downward. Can I pause this? Okay, I can't pause. Okay, I'll keep going. So now I have my free body diagrams drawn. So now for the first example, I'm going to make an equation using Newton's second law for each mass. So let's look at the first one. So I have F net for the first mass is equal to mass 1 times the acceleration. Remember, the acceleration is the same for both masses, so I'm just going to write A. I don't need the subscript. And then I'm going to add up all the forces in the left-right direction. So I have Ft plus Fk. Now, we should define some directions. Here I'm going to define to the right as positive, and I'm going to define down as positive here. So this is the same. Remember, the pulley changes my direction, so this is positive and down is positive. In that case, then I have 2.3 A to the right, because I know we're accelerating to the right, Ft is going to be a positive value, and then I have to subtract Fk, because Fk is going in the opposite direction. Now this is similar to question 1. I have to sub in some values. Well, can I figure out what Fk is? Well, I sure can. I can use the Fk formula, so that's mu k Fn. Can I figure out what Fn is? Oh, sorry, this is Fn1. 1. Should keep my subscripts. Mu k I know, and Fn1, well, I can figure out Fn1. It's the same as Fg1, or the force of gravity. I can do that off to the side here. Fn1 without a arrow, because we're not looking at the vector, we're looking at the magnitude. This is equal to Fg1, which is equal to m1 times g, which is equal to 2.3 times 9.8. Very cramped solution here. 2.3 times 9.8, which is 22.54 newtons. So we end up with 2.3a equals Ft minus 0.45, 22.54. Okay, so I get 2.3a is equal to Ft minus 10.143. I get Ft is equal to 2.3a plus 10.143. Okay, that's my first equation for my mass here. Now I'm going to try to find make it a similar equation for this second mass. Why don't I do that up here? I'll have a bit more space. F net 2 is equal to mass 2 times acceleration, which is equal to Fg2 plus Ft. That's just adding up all the vectors. Now I can do some directions. So I have 3.8a. I know a is downward, which I've defined as positive. The pulley just changed that direction. Then Fg2 is going to be, well, that's going to be m2 times g. I can figure that out easy enough. And the tension is backwards, upwards, so it's negative. So it's negative Ft. We don't have an arrow because this is now a magnitude, which I've assigned a direction. I can sub in some values here. .8 times 9.8. 3.8a is equal to 37.24 minus Ft. If I bring this to the other side, I get Ft is equal to 37.24 minus 3.8a. Oh, okay, so now look, I have one equation here, and I have two equations here, and they have the same, the two same variables, so I can solve using my grade 10 math ideas. I'm going to use substitution, set Ft equal to Ft, so I have 2.3a plus 10.143 is equal to 37.24 minus 3.8a. I guess I should write set 1 equal to 2 or something like that. Okay, now let me collect my like terms. So I get 2.3a plus 3.8a is equal to 37.24 minus 10.143. Have this number in my calculator still. So I end up with 27.097, and 2.3 plus 3.8 gives me 6.1a. I divide 27.097 divided by my answer, and I get a is equal to 4.442. Okay, does that number make sense? Yeah, I guess it should be accelerating with a certain small amount. Therefore, the acceleration of the cart is 4.4 meters per second squared to the right. And it's not asking for it in the question, but we know that the acceleration of the mass is also 4.4 meters per second squared, but it would be down in this case. One last caveat to talk about is in your textbook, you'll see solutions that look a little different from mine, where they will make a system. They will combine the masses and make a system. Again, this is a very confusing method that I advise against. Me and Mr. Lupo both advise against it. It's more methodical, it's more reliable to make a free body diagram for both blocks, and then to make an equation for each, and then to solve the system of equations. There's less chance you'll make a mistake as you go through these problems. So you can use whatever solution works for you as long as you get the correct answer. Good luck with these questions, and until next time.